I'm Jim Thatcher from Oregon State University, and I'm presenting an in-progress pilot project supported by the Transdisciplinary Innovation Research Program at OSU, with work done by cartographers at OSU, the University of Oregon, and Texas A&M Galveston, as well as mathematicians at OSU and a data scientist with the American Institute for Research. This is still very much an in-progress pilot project, so we welcome your feedback and suggestions. It's also an attempt to work across the disciplines of cartography, data science, and mathematics. So to give a rundown of the presentation, first I'll give a bit of background on maps and disasters. This isn't meant as a comprehensive overview, but rather of where we are situating our work and the ideas we are drawing from to create it. That part of it is an in-progress literature review piece. Then I'll touch briefly on the current computational costs of generating on-the-fly routing updates and how these costs impact the use of such systems in emergency and disaster situations. Then I'll introduce how the field of mathematics, a subfield called Topological Data Analysis, from here on I'm going to call it TDA to save myself that mouthful, and discuss how it applies to dynamic routing situations. We'll then try to pull everything together to describe how our solution performs under the type of dynamic pressures that one finds in emergency and disaster situations. And I'll end on a more positive note, discussing our next steps, as well as some of the lessons we learned in trying to bring advanced computational mathematical approaches into a geospatial and cartographic system of representation. So I'd like to give a very brief overview of the cartographic work on disasters that we draw from in terms of framing and situating our own work. We've just broken it into 4 heuristic categories. So the visualization of disasters and risk writ broadly, the use of scale and dimensionality in understanding and communicating disasters, uncertainty, and finally, issues around community engagement and the co-production of knowledge. Looking at how cartographers have visualized disasters and risk, we see that they occur in many different map types, from state-mandated risk maps to national-level assessments to large-scale pre-event planning maps. Across these cases, we found an overarching emphasis on how the symbology of these maps impacts their ability to communicate effectively in their chosen situation, whether that be a small-scale evaluation of risk at the state level to a large-scale evacuation route for a coastal town. Color, size, shape, those classic elements of cartographic praxis come to the fore, either through interpretive studies that examine how supposed map readers make use of the map, or through the creation of idealized frameworks for such communication, with the latter often built from the former. More specifically, with respect to scale and dimensionality, literature similarly tends to emphasize the use of the maps, how accurate they are in terms of measurements, at what scale they are useful for the readers to access, and so forth. This sort of makes sense in disaster planning. Another major area of research into the mapping of disasters is around uncertainty. As Kostelnik et al. Put it, the entire subfield can ultimately be thought as intrinsically in search of appealing yet responsible representations. While I'm personally more prone to deconstructing what this means in terms of the ontological status of a map itself, restricting ourselves towards more empirical outcomes here, we see that the uncertainty can often be thought of through the source, through its source. Is knowledge missing? Has an underlying condition changed? And so forth. The benefits and trade-offs of communicating uncertainty: if the map maker expresses too much uncertainty, will the map reader doubt the intended outcome? Here, for example, say to evacuate from a flood. Taken together, Kostelnik et al. Continue that hazard maps often are overly simplistic and do not capture the complexities inherent in risk, while Kunz et al. Worry that the lack of guidelines or codes for standardized visualizations of risks and hazards inhibits clear communication and assessment. Unfortunately, as with many cartographic quandaries, there's no simple solution. However, yet another set of research approaches these limits through processes of community engagement and co-production. In other words, if the cartographer in her studio cannot solve the issue abstractly, perhaps a more recursive praxis might. Here we found a vein of literature that seeks to balance novice and expert users through collaborative processes. Some a more traditional study of how end users interact with maps. We've all probably at least read some of these, right? That are fed into iterative design processes, and some that are truly trying to co-produce maps from the ground up. In some, these studies seek to balance the skills of the map readers with the complexity of the map itself, striking a balance that can potentially, as Liu and Palin put it, merge the professional and participatory geotechnologies towards the goal of greater response to and from disasters. So one theme throughout all of this is that disaster mapping or emergency mapping covers a wide range of potential maps, both in terms of topics, from fire to landslide to earthquake to tsunami, and in terms of use cases, for pre-planning by professionals, for pre-planning by citizens, for after the event recovery, and so forth. On the right here, we have a couple of maps from Oregon's Beat the Wave series. These maps are meant for use by the public before an event. However, during a set of recent workshops we conducted on the coast, we found that most users want to try to access them during the event, which seems a little odd, right? Like you're shaking due to an earthquake, and you're like, oh, which way do I go? In another example of the mismatch between expectations and use cases, in Oregon, there is a somewhat infamous fire risk map that the state has had to actually formally withdraw and retract. Unfortunately, due to online conspiracy theories, as well as the timing of the release coinciding with a new set of policy adjustments from major insurance agencies, citizens believed, and many still believe, that the maps led directly to insurance policy cancellations. In other words, right as this map came out, people were getting notifications that their fire insurance was not being renewed. They were not related at all, to be clear. This did not happen. It's a fiction of feverish Facebook imaginations. But it's an excellent reminder of the sorts of maps that do exist, how they are intended to be used, and how they end up being used or misused. Within this larger context, then, we decided to focus on an area that's relatively underserved in current cartographic practice: maps for use during evacuation events. One reason that these maps don't tend towards much use is precisely because maps are often static, or at least route planning is. But disaster events produce dynamic circumstances that can shift rapidly. This is where the transdisciplinary nature of our project starts to emerge. There exists a host of routing solutions today. In an earlier research project with some of these collaborators, members of this team looked at using estimated travel times between places in the United States as a means of measuring compactness of electoral districts, not through geometric measurements as the crow flies, but through estimations of how people actually move through and experience space. While a very different purpose and set of research questions, this forced us to dig deep into routing algorithms and engines, as our method required calculating hundreds of millions of travel times between centroids of census blocks. I think we ended up with something like 8 billion. In the image on the right, you can see census block groups swapping between different districts to minimize travel time between all centroids at all times. While different routing engines use slightly different algorithms, after trying most major ones, including Bing and Google, we settled on OSRM for its cost, free, and its ease of use. Our testing showed it had comparable speed and accuracy to commercial offerings whose costs at the scale we needed would have been prohibitive, like hundreds of thousands of dollars. The reason I bring this up is because OSRM, like other routing engines, ultimately relies on the sorts of traditional network distance analyses that many of us know. In OSRM's case specifically, they use variations on Dijkstra, but have set up a series of shortcuts and speed-up techniques to bring down the cost in terms of computation power. For example, OSRM has used contraction hierarchies where you can skip over nodes in a graph for over a decade now, among other more recent techniques. And these shortcuts result in an incredibly fast query time on an established graph, but they require quite a bit of pre-processing to set the graph itself up. And here we start to see the problem during a disaster. For example, while an individual query may come in well under 10 milliseconds, pre-processing a continent-sized network took us a couple of hours. The issue is that any time an underlying node on the graph is changed, the entire graph has to be reconstructed in this approach. In other words, for example, if a road closes due to a rapidly changing fire or flood situation, the entire routing graph goes down until it can be pre-processed and brought back as a reestablished graph. When constructing maps for use before an event, this is fine, right? The Beat the Wave maps for the Oregon coast are explicitly not meant for use during events, but rather to help people prepare ahead of time. However, we wanted to create tools that were usable not only before events, but could also be used by people responding to flood, fire, and other emergencies that need up-to-date and rapidly shifting routing. So we asked ourselves, just generally, it's a good question, can we do better? Could we create a fast, scalable solution that can link where people are with where they need to go during times of crisis? This is meant as a generalizable approach that could, on one level, analyze overall patterns of evacuation with respect to populations. For example, ensuring that underserved people are in able to be evacuated areas. And this picture illustrates what we came up with. I'm not going to go too much into it, because honestly, I don't do the math part. But it's a minimum cut for a given graph which equals the maximum flow value to a max flow min cut theorem. It's a relatively standard approach. It tries to maximize the flow across the network during a set of cuts made to it. And this left us with the following question. And an applied example from a 2014 wildfire, and basically this is where Oregon State is. I do apologize that the map is kind of ugly. It was made by a mathematics grad student. This image shows traffic flow, the cyan lines from one neighborhood, the green vertices, to another neighborhood, the red vertices, where thicker lines indicate greater flow. The thickest path here indicates a preferred route. And the capacity of the edges is determined by the speed limit. There we go. And so what we did here is we actually pulled some nodes off, and this rerouted the entire graph without having to recalculate it. So on the existing graph, we were able to pull nodes out. TDA allows for this, and it ended up with an order of magnitude expansion in speed. So again, this is a pilot project meant to build collaborations across the fields in order to unearth approaches that wouldn't otherwise occur. It's an attempt to take TDA, which allows us to calculate on edges as well as nodes without having to refactor our graph, and apply it cartographically, to use topological relations between and across space to better visualize and analyze the spatial worlds in which we find ourselves. I do apologize, but I'm going to end there, as I will not go over time. I've been timing myself. Sorry for looking down like that. I hope you have some questions, and it is a pilot project, but right now we're getting an order of magnitude speed increase over traditional approaches on graphs at the state size level. So, not bad. Thank you.